All right, welcome to the Explainer. Today we are diving into a really key concept from Precalculus, and that's solving systems of nonlinear equations. Now I know it sounds a little intimidating, but trust me, it's a puzzle that's being solved all around you every single day.
So, it all really starts with this one simple question. Where do curves collide? I mean, think about it. If you draw a circle and a line on a piece of paper or maybe two parabolas, where do they cross? That's the exact mystery we're going to solve today.
And look, this isn't just some abstract puzzle for math class. No way. The answer to that question is literally what powers the GPS in your pocket, the thing that pinpoints your location anywhere on Earth. So you're going to want to stick around, because we are absolutely going to show you how that works.
Okay, but first things first. Before we can get to that amazing treasure map, we got to understand the language it's written in, right? So, let's break down the math behind all this.
All right, so here's our main challenge. We're trying to find the exact coordinates where different curves smash into each other. You know, mathematically speaking, we're basically hunting for those specific x, y points that make two different equations true at the exact same time.
So what's the deal with the curves? Why aren't they just straight lines? Well, it's all about those pesky little terms like x squared or y squared. A plain old x and y, that'll give you a nice, predictable, straight line. But the second you square one of them, you're bending that graph into all those cool conic sections you learn about in Precalculus. We're talking circles, parabolas, you name it.
And this is where it starts to get really interesting. See, with two straight lines, they can only cross once, if at all. Pretty boring. But nonlinear systems, they're way more dynamic. A line might miss a circle completely, or just graze it at one single point, or a slice right through it in two spots. And get this, when you've got two complex curves, like two circles, you could have up to 4 different solutions. Wild, right?
Okay, so how in the world do we find these points without just, staring at a graph and guessing? Well, we've got a secret weapon. Our go-to algebraic tool here is called the substitution method. And believe me, it is a super powerful and reliable way to crack these systems wide open.
So here's the game plan. It's a simple 4-step process. Step 1, you're going to solve the easy equation, the linear one, for one of its variables. Step 2, take that expression you just found and substitute it into the more complicated nonlinear equation. Step 3, now you solve the new equation you just created. And finally, step 4, you back substitute. You take your answer and plug it back in to find the full XY solution pairs. That's it.
You know, the best way to really get a feel for a tool is to actually use it. So let's jump in and run through a couple of examples. We'll see this method in action, and we'll start easy and then work our way up.
All right, first up, we've got a real classic, a line meeting a circle. So you can picture it, right? We have a circle sitting at the origin, and then a simple straight line cutting across the graph. Our job? Find out exactly where they intersect, assuming they intersect at all.
Okay, so let's follow our game plan. First thing we notice is that the linear equation, y equals x plus 1, is already solved for y. That's great. It saves us a step. So our first real move is to take that expression, the x plus 1, and plug it right into the y spot in the circle's equation. This is the magic move, people. It merges our two equations into one single problem that we can actually solve.
So after we expand that out and clean up the algebra a bit, what are we left with? A standard quadratic equation. And a little bit of factoring, boom, it tells us our two possible x values for the intersection points are -4 and +3.
But wait, hold on, we are not done yet. Remember, an intersection point needs both an x time and a y coordinate. So we take each of those x values we found and plug them back into our easy-peasy line equation y equals x plus 1 to find their matching y values. And there you have it, our two precise intersection points.
Okay, you ready for another one? Let's do it. This time we've got a parabola and a line. Now, what's cool about this one is that both equations are already solved for y, and that sets us up for a really slick shortcut. So think about it. If y equals x squared and y also equals 2x plus 3, well then those two things must be equal to each other, right? So we just set them equal. It's a slightly different start, but it lands us in the exact same spot with a nice quadratic equation that we can solve to get our x values, which are 3 and -1.
And just like we did before, now we got to complete the pairs. So we take our x values and plug them back into the simplest equation we've got, which is definitely y equals x squared, to find the matching y values. And that gives us our two final solutions.
All right, time for the final challenge. Let's really level up here. The intersection of two circles.
Now, if we try to use our trusty substitution method here, oh man, it would get messy, fast. We need a smarter, more elegant way to tackle this one. This is where we pull out a different tool from our toolbox. Take a close look at those two equations. See how they both have a y-squared term? That is a huge clue. It's the perfect setup for a technique called the elimination method. All we do is subtract the entire second equation from the first one. The y-squared terms just poof, they cancel each other out. And just like that, a really complex problem becomes a simple one we can solve for x. So, we take that x value, we plug it back into one of the original circle equations, and we solve for y. What we get is that y squared equals 41 over 9. Now, pay attention, because this is a super important step. When we take the square root to get y by itself, we have to remember both the positive and the negative answer. This is crucial. It gives us two different y values for that one single x value.
Okay, so we've seen a few methods in action, which is great, but now let's talk about a couple of common traps that people fall into all the time. Seriously, just knowing about these can save you a ton of headaches and, points on a test.
We actually just ran into this in that last example, and honestly, it is by far the biggest mistake people make. Whenever you have to take the square root to solve for a variable, like y squared equals 9, you have got to remember that there's a positive solution and a negative one. It's not just 3, it's plus or minus 3. If you forget one, you've literally only found half of the answer.
And my second big tip for you is this. Once you think you have your final answers, take 30 seconds and plug them back into both of the original equations, just to check. If your XY pair works in both, you know you've absolutely nailed it. It is the best safety net for catching any little algebra mistakes you might have made.
Okay, so we've covered the what, the how, and the what to watch out for. But I bet you're still asking that big question, right? When on earth would I actually use this stuff outside of a math classroom?
Well, let's circle all the way back to the beginning, because the answer is probably hidden inside the very device you're watching this on right now. Yep, this is the secret math that makes your phone's GPS work.
So here's the basic idea. You've got these satellites orbiting the Earth, right? And they're constantly sending out signals with their position. Your phone picks up signals from at least 3 of them and calculates how far away it is from each one. Now, each of those distances creates a giant imaginary sphere, with the satellite at the very center, and your phone is somewhere on the surface of that sphere.
And there's the aha moment. Figuring out that one single point in space where those 3 giant spheres all cross, that is solving a system of 3 nonlinear equations. Your phone is a little math genius. It crunches all those numbers in a split second to figure out exactly where you are on the planet.
So the next time you pull up a map on your phone, just take a second to remember the incredible math, that elegant collision of curves that's making it all possible. It really makes you stop and think, doesn't it? What other amazing hidden math is secretly running the world all around us?